Hello everyone and welcome back to another minute concept, or rather in-depth concept on physics, this time about dynamics problem solving. So this is the culmination, or not exactly culmination, but instead the combination of all of the things that we've just learned. So from the difference between kinematics and dynamics, to free body diagrams, to the different laws of motion, this is where they all come together. Since dynamics, it really encapsulates all of those in the sense that they all work together to understand the motion of an object. So, with that in mind, if you guys need a bit of a refresher, feel free to go back to those videos first. But now, let's just get straight into it. So, in solving problems involving dynamics as seen on the screen, you need to visualize the situation first and make the right free body diagram. Based on this question that's been given to me, this is already done for us, as seen here. And next is we have to determine all the forces involved. Both non-contact and contact forces apply unless stated otherwise. So of course, unless the question says, for example, exclude friction, then that's when you're not supposed to include it. However, if the question doesn't say anything, just assume that it exists. Okay? So let's try understanding this first question. Oh wait, and the final step, sorry. Based on the given and the required to find, use either the second law of motion or the kinematic equations. And why the kinematic equations? I'll explain that with this question in a bit. So let's get into it. A box of mass 2 kilograms, or 2.0 kilograms rather, is pulled up a ramp that makes an angle of 15 degrees to the horizontal axis with a constant force of 8 newtons. The box starts from rest and travels a distance of 0.50 meters in 3.8 seconds. Find acceleration, the component of weight on the box parallel to the ramp, and the magnitude of the frictional force on the box, as well as the coefficient of dynamic friction. Okay, so that's kind of a lot. Now, where do we start here? We can start with the easiest to find, which is our acceleration. So how do we know that that's the easiest to find? Well, based on the question, we have a constant force. Now, if you recall, the formula for force is mass times acceleration. Now, if this force is always the same and never changing, that means these two are also never changing. And if there's no changing acceleration, we can now use our kinematic equations. Our kinematic equations apply for UAM, or uniformly accelerated motion. And this is why it's important to understand the question first so that we can take the shortcut. Well, in essence, this is the best method, right? So without further ado, let's try using our kinematic equations. So if you recall, we have 4. The first one is Vf is equal to V0, or initial velocity, plus acceleration times time. We have delta x is equal to Vf plus V0 over 2 times time. We also have delta x is equal to initial velocity times time plus 1/2 acceleration times time squared. And we also have final velocity squared is equal to initial velocity squared plus 2 times acceleration and delta x. Now, our given is only the distance. We have the distance, which is... Wait, let's put these all together. Okay, let's put this here. Now we have to move the screen. Let's put these guys like right... No, let's just remove this one already. Oops. Okay, so we'll put this up here so that it's easier for everyone to see. Okay, so our given based on this question is... Hold on. There. Okay, so our given is delta x, which is 0.5 meters. We're also given our time, which is 3.8 seconds. And we also have our initial velocity, which is 0 meters per second because it starts from rest. Now, which of these equations should we use? Well, if you guys recall, there is actually an easy way to determine which equation to use. So every kinematic situation, again, as a review, they should give us at least 3, and one of them will intentionally be missing, and you will also be solving for another variable. So in this first one, there is no delta x here. No delta x. In the second one, there is no acceleration. For the third one, there is no final velocity. And the final one has no time. So since we're looking for acceleration, we need an equation that involves acceleration. So definitely not the second one anymore. This guy is gone. Okay, here. And we're also looking for an equation that does not involve final velocity. So these two are gone. These two are gone. So now obviously we're going to have to go with equation 3. So let's just get rid of everything else here. Since this is just a review, that's not going to really be needed anymore. Okay. So this is our kinematic equation that will be used. Now let's plug in our values. So based on the values given, all we're going to do is plug in, and let's try. So let's use the blue pen. So delta x, which is 0.50 meters rather, times is equal to 0 times time, which is just 0, so we're going to get rid of that, times 1/2 a times 3.8 squared. Okay, so putting it into our calculator, 3.8 squared is 14.44, which is divided by 2, that's 7.22 a, since a is what we're looking for. Now we're going to divide both sides by 7.22, which leaves us with 0.5 divided by 7.22, that is 0.069. 0.069. There, okay. That is 2 significant figures, since that's the least amongst the given. And yeah, so our acceleration now, let's give it a unit. Let's get rid of everything else here. Or actually, let's keep the given. Okay, we'll get rid of this equation. We'll shrink the given. Our new acceleration is going to be 0.069 meters per second squared. Or, okay, let's just rewrite it. 0.069 meters per second squared. Okay, so now that we've done the first RTF, we can move on to the next one. Okay, so now that we've gotten our acceleration, we need to find the next RTF, which is the weight of the box parallel to the ramp, or the component of weight which is parallel to the ramp. Okay, so as you can see now on the screen, I've made a new version of our drawing. Now, why did I draw it like this? This is our new Cartesian plane. So our original would probably look like this. Let's show it here. Our original Cartesian plane would probably look like this. So, the simple, top to bottom, left to right. However, that would actually be less in our favor and make things a bit more hard to visualize. Let me explain. So, gravity works straight down, right? Straight down to the Earth, the direction of the Earth. In other words, this box is gravity. From its center, will be working straight down. Now, the reason why we're trying to get the Cartesian plane to tilt is so that we can actually find its components that aren't going straight down. Because the box is on an incline, this vector right here is actually a resultant of 2 different vectors, an x and a y component. And this can be seen because this arrow over here, this isn't just the top of our Cartesian plane. This is actually the vector arrow for our normal force. our normal force is going to be going up at an angle simply because the box is resting on an inclined plane, meaning our box is not going to be experiencing a normal force going up like this. Our box's normal force is always going to be perpendicular to the surface it's resting on. That is the definition of a normal force. So now, where do we go with this new information? So based on this new information, we can now actually create our own new triangle, right? So this triangle here, this triangle formed by the ramp, that's already set, right? That's given to us, which is good. And the angle is also given to us. What are we looking for? We're looking for the component of the box parallel to the ramp. So parallel to the ramp. If you look closely, this x-axis here is showing the incline of these said ramp, or the ramp in question. So all we're going to do is essentially we're just going to copy this line. We're lucky because we're on a computer. We're just gonna copy this line and make a new one here at the bottom. Same angle and everything. That's the beauty of technology. It actually helps us visualize, right? So there's our new line. Now what do you guys notice? We have a new triangle here in the middle. Like right here, this is a new triangle. So with this new triangle, we're able to solve for the missing components that I mentioned earlier. The components of the weight that make up its straight downward vector, which is its resultant. Now the question is though, how can we solve for it if we don't have the angle of this triangle? Well, the angle is actually given. The angle is going to be 15 degrees. Wait, let's use a different pen. Let's use blue. This angle right here, no, I can't see blue. Yellow? Okay, this angle right here is 15 degrees. Okay, so if you guys can see it, let's remove that. Wait. Okay, there. That why is that there? Okay, anyway, there. This angle here is 15 degrees. Simply because these triangles are similar to one another. If I flip this to its side, we will get a very similar triangle. Well, not just very similar, like literally a similar triangle to the one that's made by the ramp. So now, just like any other vector component question, we have to go back to solving for the different vector components. And in order to do that, we need to first identify the different parts of our triangle. Okay, so now to identify the different parts of our triangle, we're going to need to use our angle as a reference point. Now, we're given our hypotenuse already. Our hypotenuse is always the resultant. And since we describe gravity, or the weight itself, mg, to be the to be the resultant, that means that this is going to be our opposite and this is our adjacent side. Okay, let's make this green pen. Opposite and adjacent. So excuse me. We're going to be using trigonometry again in order to solve for our weight components. And in order to solve for weight parallel, we're going to be concerned with the opposite side. Now, before we get started with that one, let's recall first what the formula for weight is. Weight is mass times gravity, right? And mass times gravity, this will give us our answer for the resultant, or the purple line. However, we're not looking for the purple line, we're looking for the white line. So we're just gonna alter this a bit and make it in terms of our vector component. So our vector component here will be labeled as W par times G par, is equal to mass times G par rather. And what is G par? Okay, so we can visualize this triangle here as both the triangle of vectors of the weight as well as the acceleration of gravity. So in order to get the opposite component, or the x component of our, or rather no, y component of our gravity, since we're working with sine here, gravity that's parallel will be equal to gravity times sine theta. So this is our g bar. Okay, and plugging that into our working equation, we'll be getting w bar is equal to mass times sine theta of g. And our theta here is 15, so let's just rewrite this with our given. Our mass is 2 kilograms. And our sine is sine 15. Parenthesis. Our gravity is 9.8, which will give us a 5.07 Newton force or weight parallel to the incline of the ramp. So that gets us our final answer. So what do we do again? Basically, what we just did was we tilted the axis or the Cartesian plane so that it would be more suitable to the question. In other words, we aligned our Cartesian plane with the ramp. And from aligning the Cartesian plane to the ramp, we were able to figure out the component of weight, which is parallel to the ramp, by simply getting vector components. And we made our new triangle in order to help us do that. So our triangle here has the purple line being the resultant vector of gravity, which is just mass times gravity. Resultant vector of weight, rather, which is mass times gravity. And we made our second line, which is parallel to the ramp, by just copy pasting. But obviously on paper you can also just imagine that that's parallel. It doesn't have to be perfect. We used our trigonometric identities to help solve, and now we got to 5.07 newtons. So with that in mind, let's now go to the next question. Or not next question rather, but the next given. So I've prepared a more summarized drawing because this drawing is going to be a bit confusing if we're going to use that one. So this is now a summation of what we currently have. So we have our force applied, which is 8 newtons. We have the 19.6 newton weight, total weight. This is our 5.07 newton component for our weight. And we're lacking out, we didn't solve for mg cosine, which is our our y component here, using the Cartesian plane of course as reference, our y component. And we're supposed to now solve for the magnitude of frictional force, which is essentially this. Let's use another white line. Or no, not a white line. Let's use a blue line. So from here to here, this is friction. So where do we start now? Based on the question, it kind of seems like we have nowhere to begin. Well, we're just going to recount the laws of Newton. So the laws of Newton says that the summation of forces should be equal to mass times acceleration. So we can start with this first. The summation of forces should be equal to 2 kilograms times our derived acceleration, 0.069. So let's try and put it into our calculator. 0.069 times 2 is 0.138 newtons. So our forces should have a sum of this. Okay, so let's take note of that. Let's shrink this. And now let's analyze our given. Okay, on the y-axis here, we can see that mg cosine and the normal force, they actually are perfectly aligned, right? And this makes sense because the normal force is essentially a consequence of the force of gravity or the force of weight. And since these two will cancel out, these two are supposed to be opposites of one another according to the third law of Newton. That means we don't have any forces acting on the y-axis. Okay, so these guys cancel out. The normal force plus mg cosine theta are equal to 0. Therefore, the summation of forces on the y-axis is equal to 0. Okay, so that means we have a we have one complete axis to not pay attention to. We made it that much simpler. Okay, so that means the only area where forces are really being involved in now, in helping us solve for this, is the x-axis. And let's count our forces on the x-axis. So, based on the diagram that we have here, our forces on the x-axis, or our summation of forces here, should be equal to the force applied minus friction, since that's a counteracting force, and that's also going to be minus our force that is parallel to the ramp. Now, why does it need to be minus the force parallel to the ramp? Well, that's because that's the component of weight. That's our component of weight that lies on this axis, the x-axis. So we're supposed to remove as well, we're supposed to add the negative value of weight on the x-axis, because these two will combine as the counteracting force of the force applied. And how does that make sense? It's simply because our force here, here on the left side, the frictional force, is aided by weight. In other words, this parallel arrow here, wait, let's ungroup this. How do we ungroup? Okay, there. So this arrow over here can actually be aligned because they're parallel to each other. They're both going in the exact same direction. Albeit they're not coinciding, they're going in the same direction. So this is actually also mg sine theta. So on the x-axis, these are our forces acting. We have the positive force, the positive applied force going to the right, and we have our negative frictional force as well as our negative gravitational component, or the weight component rather, sorry. So how do we move forward from this now? Let's group this again and let's move it up. Let's summarize our values. Okay, so let's get rid of this as well for now. This moves up and this moves up as well. Okay, so based on our given and what we've derived so far, we can say that the summation of forces all in all between both the y-axis and the x-axis should be equal to 0.138 newtons. And we got that based on the second law of Newton, which is the summation of forces should be equal to mass times acceleration. And we solved for acceleration in the first part of this video. So next, we were also able to determine that there's no forces acting anymore on the y-axis. They cancel each other out because the normal force and the mg cosine force rather are equal to 0. So in other words, this force over here, the summation of forces on the x-axis, this is also equal to the summation of forces in general. And why is that? Again, it's basically because the summation of forces here is equal to the forces here on the x-axis as well as the forces on the y-axis. Now, if the forces on the y-axis are equal to 0, then it's basically just the summation of forces on the x-axis. So this is now our working equation. The summation of forces is equal to the summation of forces on the f-axis. So let's solve for our answer on what the magnitude is. Is that what it's asking for? The magnitude of the frictional force on the box is. Okay, we'll just put that like here. We'll just go to that when we need it. So now it's really just math. We're going to substitute everything. So the summation of forces should be 0.138. And this should be equal to the force applied, which is 8 newtons, minus our frictional force, which we do not know, minus our mg sine theta, which is 5.07. Now, isolating friction, we just have to move everything to the other side. Or actually, rather than doing that, since friction on this side is negative, we can move it to the left. So friction is equal to, we'll also be moving 0.138 to the right, is equal to 8 minus 507 minus 5.07, 5.07 minus 0.138. And this should now get us an answer of, hold on, let me put it into my calculator. 8 minus 5.07 minus 0.138, that's 2.792 newtons. 2.792 newtons. There. So now we now know that excuse me, we now know that our friction, the magnitude of our friction is 2.792 newtons. And if we're going to follow significant figures, we're following two significant figures here, since apparently this 8 is not just 8, it's supposed to be 8.0, sorry, 8.0. So we're going to be following two significant figures. It's 2.8 newtons. There. So yeah, that's our answer for the third required to find. So to recap, what we did was we just analyzed the given problem and we isolated which forces need to be added together. We started off first by determining what the summation of forces should actually amount to, which is 0.138 newtons. And from determining what it's supposed to end up as, it's going to be a lot easier to find what's missing. So we started off with the y-axis, which is the normal force and the mg cosine theta. Mg cosine theta, again, for those who might have forgotten, that's the component of weight that we did not solve for. We didn't need to solve for that anymore because if you look again, they're actually on the same axis. They're perfectly straight with one another and they're supposed to be opposites. So whatever the value of mg cosine theta is, the normal force should be the exact same magnitude but a different sign. So they completely cancel out. And this is because of the third law, which is the action-reaction law. So that brought us to the conclusion that the forces on the y-axis are equal to 0. So they technically don't matter. And since that's equal to 0, that means the only axis that we really need to care about is going to be the x-axis, which is why we were able to arrive with this formula here. The summation of forces should be equal to the summation of forces on the x-axis. Now, we isolated the x-axis first to determine what should be included in the first place. So the x-axis contains our applied force of 8.0 newtons, our frictional force, and the force that we got a while ago, which is the component of weight parallel to the ramp, which was 5.07 newtons. Now from there, we were able to substitute everything. We got to this point of the equation, and we were able to determine that the frictional force is equal to 2.8 newtons. That's the magnitude. And from here, actually, it's going to be a lot easier to solve for the last part. Though now we're actually kind of forced to solve for mg cosine theta. So allow me to explain again. Our final question here, wait, let's put our givens together again. Here, hold on, okay. Okay, so frictional force is given to us by this formula. Friction is equal to the coefficient of dynamic friction times the normal force. And we didn't solve for the normal force. So what do we do now? Well, we just go back to our definition of normal force. So a while ago, I told you guys, literally just now, that the normal force is the same as mg cosine theta, except it's a negative symbol, or it's the complete opposite. So why is this so? Let's again recall an example, as a very simple example, a box on a table. The box exerts a force on the table going down, and the table exerts a force on the box going up. This is the normal force, the one going up, and the weight is the one going down. So they're just complete opposites. So in order to solve for the normal force, we just need to solve for mg cosine theta. And this shouldn't be that hard because we know already what to input. So mg cosine theta is also equal to 2 times cosine 15 times gravity, which is 9.8. And that's supposed to be equal to 18.9 newtons. 18.9 newtons. Okay, there. So our normal force can be described like this. The relation between normal force is equal to the negative mg cosine theta. This is a negative symbol, by the way, because it's supposed to be negative 9.8. And our normal force is now going to be positive 18.9 newtons. So let's put this here on the side. And there, 18.9 newtons. So if we plug in our values, we're going to get 2.8 is equal to coefficient of dynamic friction times 18.9. Okay, let's use a different color pen since it might be a bit confusing. Okay, again, 2.8 is equal to 18.9 mu. Okay, so now isolating mu, that should get us 2.8 divided by 18.9, and that should be 0.15. Let's double check that just to be sure again. Divided by 18.9. Yes, 0.1481481 repeating. So two significant figures again, 0.15. So our final answer for this one is 0.15. That is the coefficient of dynamic friction. And the coefficient of dynamic friction is actually one of the most important formulas to remember, especially in high school level physics, because this is supposedly one of the easier portions to get once you've solved for everything else. So it would really be a shame if you were able to solve for everything but then forgot about this. So if you want to remember the formula, it's just this. Friction is equal to the coefficient of dynamic friction times the normal force. Of course, if the question gives you the normal force and the coefficient of dynamic friction, then you don't need to go through everything that we just did to solve for friction. So yeah, that's basically it. To recount what we did for this final part, we used this formula and we derived first our normal force, and then we solved for friction. So thank you everyone for watching this in-depth concept. It may be a bit confusing. That is sure. That is for sure going to be a bit confusing if it's your first time trying it. That's why I suggest you guys should try to review sources on the internet that have like practice questions. I'll be leaving a link in the description, links in the description for websites that have practice questions as well as the answers to those questions, so that maybe you guys can have some more practice. And another tip is don't forget the laws of motion, as well as the basics of kinematics and the basics of free body diagrams, because they will really help a lot. And lastly, be creative, because if you're not creative, you won't be able to think of a solution like this. You won't be able to get to this type of drawing. You're going to need to think outside of the box in a way where you're going to be twisting your view of the object and stuff like that. So don't limit yourself to what the question's given, and of course if you hit a roadblock, then what other choice do you have than to look at it differently? So that's all, everyone. Thank you for watching, and if you have any questions, feel free to leave a comment so that I can help you out in the comment section. So I hope this helps, and I'll see you guys in the next video or videos about physics. Thank you, everyone, and goodbye.